Wonderful. We are recording. I want to say, everyone, welcome. I'm very happy to have the very first a TCS Plus talk of the term. I want to say to the audience, if you want to ask questions during the talk, and please do, type them into the chat, and I will then relay them to our speaker. If you have a short clarifying question, I will ask it immediately. If you have a longer, a discussion question, I'll probably hold that until the end. I will have time for some questions there. This is being recorded. Great. And it is my absolute pleasure to introduce our first speaker, who is both a collaborator and a friend of mine. And so this is an extra special pleasure. Audra McMillan, who is currently a research scientist at Apple. She works extensively on things in the space of privacy preserving machine learning and stats, especially in the context of a differential privacy. Before she was at Apple, she was a postdoc at BU and at Northeastern, and she got her PhD in math at the University of Michigan. And she will talk today about some of her recent work titled Differential Privacy in the Shuffle Model. Take it away, Audra.
Hi, thanks for the introduction, Rachel. So as I said, my name is Audra McMillan. I'm a research scientist at Apple, and today we're going to be talking about joint work with my colleagues Feldman and Talwar. I'm not going to be assuming any background in differential privacy, but do ask clarifying questions if you're unfamiliar with it as we go along. Okay, so differential privacy is a notion of privacy for machine learning or statistics. So imagine we have our data subjects, and our data analyst is trying to learn some function of our data subjects. So you can imagine this as a machine learning model or some statistic about them. And, okay, but we care about the privacy of our data subjects. So differential privacy is a particular way of defining privacy in this context. So suppose I have two data sets, P and P prime, and these data sets are exactly the same, except in the data of a single individual. So in P, the third person is green, and in P prime, they're pink. Now imagine we run an algorithm on P or P prime. Then the guarantee we're going to have from differential privacy is that from the output A of P, it's impossible to confidently guess whether the input was P or P prime. So it's impossible to confidently guess whether my data was green or pink. Okay, so what does it mean to not be able to confidently guess from the output what the input was? So in order to define that, we're going to need a notion of closeness between two random variables. So we're going to say two random variables, x and x prime, are epsilon delta indistinguishable if for all events in the output space, so all possible outputs from a selection from x or x prime, the probability of that event is about the same given a draw from x or given a draw from x prime. And by about the same, I mean a multiplicative factor of e to the epsilon. So if epsilon is small, e to the epsilon is about 1, and an additive factor of delta. And we're going to picture delta as being extremely tiny. So say 10 to the negative 6, 10 to the negative 8. So very, very tiny. Epsilon, we can picture more in the 0.1-ish range. So that thing is about 1. And so now, if I'm given the draw from either x or x prime, it's impossible for you to confidently guess which random variable is drawn from, because the probability of the output was about the same under either of them. Okay, so coming back here, so we want to formally define what it means to be able to not confidently guess. So we're going to say an algorithm A that goes from a data set into any output space is epsilon delta differentially private if for all possible pairs of P and P prime. A of P and A of P prime are epsilon delta indistinguishable. Okay, so if they're epsilon delta indistinguishable, we can't guess which one was drawn from, so we can't guess what the input was. And our hope, of course, we still want to do good data analysis. So our hope is that we can design an algorithm A of P, where A of P is close to the statistic we wanted to compute, or the model we were trying to assign F of P. Okay, so this is our goal. All right, so just as one example of how you can achieve this. So suppose I have some statistic F that I want to compute. And F goes into, so Y, sorry, it should be written here, Y is R back to Euclidean space. And I have the guarantee that F of P and F of P prime are within distance 1 for any pair P and P prime. Then the following algorithm is differentially private. I'm just going to add Gaussian noise. So if I add Gaussian noise with standard deviation sigma, then adding Gaussian noise satisfies this privacy guarantee, where notice that the wider I make my Gaussians, the more private I get, the more these Gaussians overlap, the harder it is for me to tell which one was sampled from. The smaller sigma gets, the more narrow my Gaussians get, the easier it is for me to tell them apart. Okay. And if P and P, F of P and F of P and F of P prime are close enough, I don't really have to add a lot of noise to be able to achieve this. And I still get a pretty good signal of what F of P was. So I'm still doing good data analysis, but I'm also protecting privacy. Okay, so a brief outline of this talk. So I'm going to be introducing a notion of privacy called the shuffle model. And then we're going to be proving some results about it. I'm actually going to go through the proof in quite a lot of detail in this talk. This is for two reasons. The proof has some practical implications that I think are interesting. Also, I think it's a particularly kind of nice, elegant proof. And so hopefully you will agree. All right, so let's explain what the shuffle model is. So the notion of differential privacy I just introduced is actually what is commonly called the central model of differential privacy, where I assume that I have a central server who I trust, and all of the data subjects send their real data to the central server. And what I care about is the privacy of the output of the central server. There's another common notion of differential privacy, which is called the local model of differential privacy, where I don't trust my central server. And so all my data subjects are going to privatize their data point before they send it to the central server. And I can talk about interactive algorithms here as well. All that's important is that every time that the data subject communicates with the central server, they send a differentially private version of their data point. And just to be completely clear, what it means for them to communicate a differentially private version of their data point. So we're going to call an algorithm A that just goes from the space of data points to some output space. We're going to say it's an epsilon delta local randomizer if for any two data points x and x prime, A of x and A of x prime are epsilon delta indistinguishable. So this is exactly the same as the definition of differential privacy we said before with size 1 data sets. And of course, we could hope that A of x is close to F of P. That doesn't make sense. So what we hope is that we can post-process the collection of local reports to something that is close to the statistic we wanted to compute. Okay, so we have two different trust models here. And most industrial applications are actually in this local model. So there is, I require a lot less trust here, which is desirable. Also, I require trust in kind of fewer places. So I don't need to spend as much cryptography protecting my data points when they're in being communicated to the central server, because I already have some privacy there. I also don't need to worry so much about where my data is being stored, because it's already stored in a differentially private form. Yeah.
We have a question, if I can intrude, Audra. Someone asked, at the big picture level, how is differential privacy as defined here different from, say, a cryptographic hash or some one-way functions?
Yeah, so it's very different to cryptography in that the output is like, so it's protecting in a different place. So I can think of them as kind of working together. So for example, in the central model, I might want to encrypt my data points as they're being communicated to the central server, which would give me, say, cryptographically no information about them. But once they got to the central server, I would want to decrypt them to do whatever I wanted with them. And I can release the differentially private thing to the data analyst. And it's like it's a thing that looks like the thing I want. So say if I'm computing a mean, it is like a number that is close to the true mean. So it's protecting in a very different place. Okay, feel free to jump in if that didn't answer the question, but I'm going to keep going.
Oh, and we have one more question that I think you might be about to answer. Okay. It says, so is the difference between global and local, the domain of A is D instead of D to the end? And does the size of the data set make it harder or like easier to get privacy?
Yeah, so the size of the data set makes it easier. So the bigger your data set is, the more accurate answers you can get differentially privately. And that is a really important thing that I guess is going to come up here. But yeah, definitely the bigger your data set is, the more you kind of other data points you have to hide among, and the more accurate results you can get differential privacy in both the central and the local model. So I'm going to say now the effect is amplified a little more in the central model. And that is sort of the difference between the two models. In the local model, everyone uses these local randomizers whose input is their single data point. But we still need an algorithm that post-processes all of those local reports into the final estimate. Okay, so we have these two trust models, and we really prefer to work in the local model because of the weaker trust assumptions, but it actually comes with a pretty high cost in accuracy. So suppose that everyone has a data point between 0 and 1, and we're just trying to compute the mean of those data points. Then in the central model, I'm going to pay error about 1 over epsilon n. And in the local model, I'm going to pay error about 1 over epsilon square root n. And this is a pretty sizable difference and can be of practical significance. Okay, so we pay a lot for the accuracy to use the local model. So the question obviously arose, can you get the accuracy benefits of the central model without the strong trust assumptions that it needs? So maybe coming back to the question before, one thing you can think about is multiparty computation. So if I could use multiparty computation to simulate a central DP algorithm, then that wouldn't require the trust assumptions of the central model. But if I could do it, properly, I could get the accuracy benefits of the central model. And this can be done in some contexts, but it's not an optimal solution. Multiparty computation is often inefficient. And the bigger thing is that it really requires tailored implementations for every statistic you want to compute. And that's just hard to implement in practice. So we want another solution that is a little simpler to implement. And this is going to be shuffling. So there was some intuition that kind of already existed that anonymity gives you privacy. And there are lots of examples of places showing that anonymity on its own doesn't give you differential privacy. So if you don't do anything else, everyone just tells you their data point, but you forget who's who. That actually doesn't give you any really meaningful privacy guarantees. But what if we combined anonymity with, say, some level of local differential privacy? Could we get something better? So this led people to introduce the shuffle model. So the shuffle model was introduced in a series of papers in 2019. And what we're going to do is we're going to add an extra server between our data subjects and our central server. And this server we're going to call the shuffler, and we're going to trust them with the real data points, or at least cryptographic versions of the real data points. And what they're going to do, they're going to do a very simple task. They're just going to take in all the data points and permute them or shuffle them. And then they're going to send the permutation of the data points to the central server. And our hope is that they don't need to be as noisy as they would need to be in the local model in order to get a good privacy guarantee. And again, I can have interactive algorithms here. This is important if you want to do something like SGD to be able to do interactive algorithms. And all that's important is that the central server doesn't know who they're communicating with. So they can still make adaptive decisions about what questions they ask, but they just can't know who they're asking that question to. All right, so it may seem like we've just shifted the trust from the central server onto the shuffler. So why is this any better? And the answer is actually cryptography. So because the shuffler is doing something really simple, they're just permuting the data points. They can, the data points can be encrypted on their way into the shuffler and then decrypted on the central server. So the shuffler never needs to see unencrypted data. The central server never needs to see unshuffled data. So as long as the unshuffled data, as long as the shuffled data has good privacy guarantees, we're protected against both of these servers individually. If they collude, then we kind of collapse back into the local model. But as long as we trust they're not going to collude, we have pretty strong guarantees against both of them. Okay, and the question of privacy amplification by shuffling. So the model I just said nothing about the data subjects needing to use local DP randomizers to communicate their data to the shuffler. But the question of privacy amplification by shuffling is, what if they do? So what if each data subject communicates with the shuffler via an epsilon 0 DP local randomizer? Then how much more privacy are we getting from the anonymization? And so these two papers that introduce this model said it quite a lot, that the output of the shuffler is a lot more private than the local randomizers were by themselves. So if epsilon 0 is small, say less than 1, then both of these functions are about epsilon 0 over square root n. And this first one is saying that for any adaptive shuffle, so any adaptive algorithm between the data subjects and the central server that goes through a shuffler gets this type of amplification. The second line here is saying that for a particular algorithm called binary randomized response, we get this slightly different formula that also in this epsilon 0 small range is about epsilon 0 square root n. So if we've got, say, 1 million or a couple of million data subjects, we're really getting a considerably smaller privacy guarantee after shuffling. Okay, so when epsilon 0 is small, these two formulas are about the same. When epsilon 0 is larger than 1, there is an exponential gap between these two results. So if we use binary randomized response, we have a 0.5 on this exponent. And the general result just has a 3 here. And I said earlier that we typically want to think of that privacy parameter as being pretty small. But notice that because we're amplifying these epsilon 0s to get epsilon, the post-shuffle privacy, if what we really care about is epsilon, not epsilon 0, then this amplification gives us a reason to use large local epsilons. So we can think of the local privacy guarantee as kind of a backup privacy guarantee. And the thing we really care about is the shuffle privacy guarantee. So we really do care about this regime where we have larger epsilon. And so we have this exponential gap in that regime. So the paper I'm going to be talking about today, we close this exponential gap. So we show that you can get that 3 down to a 0.5. It was actually gotten already down to like a 2.5 in some intermediate papers. And in some special cases, it was gotten a little lower. But we can get it all the way down to 0.5 in the fully adaptive shuffle model. We do a little bit more. So we show that what I just had before was everyone was using an epsilon 0 local randomizer, which means their delta in that formula I gave earlier was 0. And we showed that they can actually use an approximate DP local randomizer, which means their delta is bigger than 0. And I'm not going to talk about this k-randomized response result, but if you are familiar with k-randomized response, we get something a little better than the general result for k-randomized response, and show that particular mechanisms do actually amplify better. Okay, and I just want to point out some notable work kind of between the original results and the result I'm going to talk about today. Okay, if you are familiar with differential privacy, I want to point out a small lie that I'm saying here, is that the amplification actually amplifies to approximate differential privacy. And so we get these extra log 1 over delta terms. I'm going to be pretty willy-nilly ignoring log 1 over delta terms in this talk. And this is because they're typically much smaller than the other terms that we're considering.
Audra, we have a question.
Yeah.
What precisely is a privacy guarantee in this shuffle model? Is it like a differential privacy for the database received by the central server, or is it a local like privacy guarantee?
Yeah, so it's a central privacy guarantee of the output of the shuffler. So if we just view kind of everything that happens until the output of the shuffler as kind of a central model algorithm, then it's the central guarantee of that algorithm. Okay, so just to hammer home kind of how good these results were, even before the paper that I'm going to be talking about, we have a graph here of the amplification. So the local randomizers here have an epsilon 0 of 6, which is pretty high. And we're going to have delta equals 0.10 to negative 6, which is pretty small. And on the x-axis, we have n's, the number of people participating. It's varying from 10 to the 5 to 10 to the 7. So kind of some realistic ranges. And on the y-axis, we have e to the epsilon minus 1, which is about epsilon. So the x-axis is approximately the privacy guarantee. And what we can see is that for all of these lines, so the two green and orange ones are from the paper I'm going to be talking about today. I'll talk a little bit later about what the difference is between them. The red line is that particular result for binary randomized response. And the blue line is the best known prior to this work. And we can see that for all of them, once n gets to be about 1 million, the central epsilons are, or the shuffled epsilons are less than 1. So we're going from 6, which is sort of maybe a too large number to meet for meaningful privacy, down to less than 1 or even less than 0.1, which is really giving us a meaningful privacy guarantee. Okay. So questions about the model before I kind of move into the proof? Okay, I'm going to move through. If you do have retroactive questions, feel free to ask as we go forward. Okay, so what I'm going to give now is some intuition, fairly detailed intuition to the proof of this result. Okay, so we're going to do a slightly simpler version. So the result in the paper that I just described is for adaptive or interaction between our data subjects and our central server. What we're going to do for the purpose of this talk is just the non-interactive version. So everyone is going to be using the same local randomizer at the same time to communicate their data to the shuffler. I do promise that it's not that much more complicated for the interactive case. It'd be surprisingly not very much more complicated, but for purpose of exposition, I'm going to do this one. Okay, so we're going to call that epsilon 0 local randomizer A. And we're going to have n people. Okay, so the first thing that we want to say is kind of a nice fact about differentially private algorithms. So A is our local randomizer, so it goes from a set of data points into our output space. And given any data points, x and x1 and x, I can do the following. So I can write A of x as e to the negative epsilon naught A of x1. And this is my privacy guarantee. So my privacy guarantee ensures that e to the negative epsilon naught A of x1 is less than A of x always. That's really kind of fundamentally what my privacy guarantee says. And some other stuff. And I can write my other stuff as 1 minus e to the negative epsilon naught times some other distribution that I don't really care what it is. It is particular to the data point x. And I just care that I can compute it. It doesn't really matter what it actually is. Okay, so this is kind of the idea that differentially private algorithms overlap quite a lot. All right. So now we're going to give kind of a rough version of the intuition and then a more detailed version. So for the rough version, imagine I have two neighboring data sets, P and P prime, and these differ on the data of the first person, and everyone else is the same, and the same in both P and P prime. Okay, so because of what we just said, I can write my randomizer A applied to the running man in the following way. So with some probability, they pretend to be the orange person. With some probability, they pretend to be the green person. And with the remaining probability, they do something that's unique to themselves. Okay, so imagine now that my green and orange people just say who they are. And everyone else samples which part of this mixture they're going to sample from. So are they going to pretend to be orange, green, or are they going to be themselves? Okay, so they sample their mixture component, and then they sample from that part of the mixture. And then we shuffle. And what we're getting from the output of the shuffler is really everyone applying this local randomizer to their data point, and then the shuffled results. Okay, but notice I can switch the order of my sampling from the mixture components and my shuffling. Because when I sampled from the mixture components, I didn't look at the history of where that data point came from. I didn't care that it came from P or P prime. I didn't care what it originally was. I just cared about which part of the mixture I was sampling from. So I can switch the order of these. And now a really important part of differential privacy is that if you take an output of an algorithm and then do some post-processing on it, the post-processed thing is only more private than the original thing was, as long as you didn't look at the data set while you were doing your post-processing. So what that tells us is that for the purpose of a privacy analysis, at least an upper bound in a privacy analysis, I can just ignore the sampling from the mixture components. That was post-processing. I didn't look back at the data point. I didn't look at whether I was sampling from P or P prime. It was just post-processing. So if I can analyze the privacy of just this mechanism here, where everyone samples a mixture component, then I'm going to get a upper bound on my privacy guarantee, or kind of a worst case privacy guarantee. Okay, so now notice that from the shuffling, because of the shuffling, the only kind of information contained in this shuffled output is the number of green people, the number of orange people, and the number of running people. So this is all of it, all the information that's contained in that shuffled output is contained in these three numbers. Okay, so now to analyze the privacy of this whole mechanism, or an upper bound on it, I just need to analyze this really simple algorithm. And so to get some intuition for why these two actually look close, let's look just at the output of the number of green people. So the number of green people in P prime is just a binomial. So all of the running people were green with probability a to the negative epsilon naught over 2. There's n minus 1 of them, so we just get a binomial. Under P, it was that same binomial plus 1, because we knew the first person was definitely green. And so now we're just looking at the privacy guarantee, or the overlap in the distributions of these two simple kind of binomial and shifted binomial. And if you remember what we said about Gaussians earlier, binomials look kind of like Gaussians. So we expect pretty good privacy between these two things, once n is large, of course. Okay, so that was our kind of rough intuition. And so let's go a little bit further into detail of kind of more formal version of that proof. Okay, so similar to in the kind of rough case, I'm going to look at just two distributions, P and P prime, and sorry, two data sets, P and P prime. And I'm again just going to assume that everyone is using the same local randomizer to communicate with the shuffler. Okay, and what I'm going to do again is reduce the kind of complicated formula we had before for A could be anything, we're going to shuffle, whatever, to this kind of simple protocol. So I'm going to say that I can reduce all of the analysis to all the people are going to choose one of three outputs, 1, 1 prime, or zeta, and send that to the shuffler. And then I'm going to prove that we can post-process those kind of simple outputs into something that looks like the output of the real mechanism. And again, because that step was just post-processing, so I do need to know the two data sets, P and P prime, but I don't need to know which one I am sampling from. I just need to know the shuffler output and the potential two data sets, P and P prime.
We have a question, Audra, on the previous slide. Can we not distinguish between the two blue people?
Here. So we get similar things in all of them. So the actual output is, of course, a multinomial, but any individual view of like green, orange, or blue is just a binomial. And actually the two blue ones are exactly the same under P and P prime. They're both just binomial n minus 1, 1 minus e to the negative epsilon naught. So they're identical. It's the distributions of green and orange people that are different between P and P prime. And the orange people have the same distribution as the green people. So it is a little bit more complicated than what I implied, but not very much. It's really just a simple multinomial that we have to analyze. Okay, so from post-processing, I again only need to compute the privacy of this really simple protocol where everyone just picks one of three outputs and the outputs are shuffled and sent to the central server. Okay, so what we're going to do now is spend some time constructing this post-processing function and proving that kind of we can reduce to this. All right, so we need another fact about differentially private algorithms. So this is a fact about a particular differentially private algorithm called binary randomized response, which I've mentioned a few times now, because I haven't actually said what it is yet. So binary randomized response is just a epsilon0 local randomizer between 0, 1 and going to 0, 1. And what it does is if your input is 0, then you output 0 with slightly higher probability. So you output it with probability e to the negative epsilon naught, e to the epsilon naught over 1 plus e to the epsilon naught. And you output 1 with slightly lower probability. And these probabilities are constructed to get kind of the maximum difference as we can while satisfying differential privacy. And you do the same thing for 1. So if your input is 1, you output 1 with slightly higher probability. Okay. And so the fact we need is that for any local randomizer that goes from 0, 1 into any output space, you can write it in the following way. So you can write it as a composition of binary randomized response with some post-processing function. Okay. So why do we care about this? So notice that in this picture in the corner, what the first person is doing. So remember, I know who the first person is. I know they're either x1 or x1 prime. And what they're doing is just binary randomized response. So if they're x1, they're reporting 1 with slightly higher probability. If they're x1 prime, they're reporting 1 prime with slightly higher probability. Okay, so I have my mechanism A, which is an epsilon0 local randomizer. And what that result I just said about binary randomized response tells us is that if we restrict A to just looking at the inputs x1 and x1 prime, I can write it in the same way. So I can imagine it as binary randomized response plus post-processing. Okay, and any function on 2 inputs, we can just imagine as having 2 distributions. So if you see the input 1, you're going to sample from Q1. And if you see the input 1 prime, you're going to sample from Q1 prime. So why we care about this is going back to this picture here. So remember, we want to show that we can post-process the input to the shuffler into all of the samples from the epsilon0 local randomizers. All right, so x1 and x1 prime are doing binary randomized response. So they're doing the first part of that composition. And now if we knew which thing that came out of the shuffler corresponded to x1 or x1 prime, so which part of where it got shuffled to, then we would know exactly what to do. We would know that at that point you just sampled from Q1 or Q1 prime, depending on whether you got 1 or 1 prime, and that corresponded to a sample from A of x1 or A of x1 prime. Now, of course, I crucially don't know which of the 1 and 1 primes correspond to the first element. So what I have to hope is that for all of them, I can sample from Q1 and Q1 prime. And if I do this, then I'm guaranteed for the first person that I'm doing the right thing. I really am getting a sample from A of x1 or A of x1 prime. And what we have to guarantee now is that for everyone else, I can kind of construct this so that I also get a sample from, say, A of x2 to A of xn. Okay, so basically, what I want to show is that for everyone else, say x2 specifically, I can write A of x2 in the following way, that they choose whether to sample from 1, 1 prime, or zeta. And if they get 1 or 1 prime, they sample from Q1 or Q1 prime. Okay, and we have to decide what they're going to do on zeta. Okay, so remember this result from earlier, that I can write A of x in the following way. So I can write it as first sampling from A of x1 with some probability, and then doing something else. We don't really care what the something else is, as long as we can compute what that something else is. Okay, so I can do this for x1. Of course, I can also do it for x1 prime. I'm going to get a different kind of something else. These are called LO for leftover distributions. And then if I average them, I get the following, which I guess we used earlier. So we sample from x1 with some probability, x1 prime with some probability, and with the rating probability, something else. And notice that these mixture coefficients match exactly to what we have in the picture in the corner. So they're exactly the probability of sampling 1, 1 prime, or zeta. Okay, but remember when I see 1 and 1 prime, I don't sample from A of x1 and A of x1 prime. I sample from Q1 and Q1 prime. But it turns out that that doesn't actually really matter. So what we proved before was that A of x1 and A of x1 prime can be written as mixtures in this way. It's another way of writing the result that we just had for binary randomized response composition. Okay, so A of x1 plus A of x1 prime is the same as Q1 plus Q1 prime, which just allows me to replace this A of x1 and A of x1 prime in this mixture with Q1 and Q1 prime. So now I have exactly what I want. I have the right mixture components, and I have that 1 and 1 prime correspond to samples from Q1 and Q1 prime. Okay, so I've confirmed now that I can do this. So now what do I do on the zetas? So for any given zeta, if I knew where it came from, I could sample from that leftover distribution. But of course, again, I don't know where the zetas come from. But what helps us is it doesn't matter. So for any zeta I see, it's equally likely to have come from x2 to xn. So they all have the same probability of producing a zeta. They all get shuffled the same. So once I see the output of the shuffler in the central server, I don't need to know which one it came from. I can just sample one of them at random. So I can sample an xi uniformly at random, of course, without replacement, from x2 to xn, and then just pretend that zeta came from that xi because it might as well have. And then I sample from the leftover distribution corresponding to whichever of x2 to xn I sampled. Okay, so now we have that for every input x1 to xn, or x1 prime to xn, we have the output of this shuffler is, or whatever thing we sample from, is corresponding to A of x1 or A of x2. So the local randomizer applied to that data point. Okay, so after this post-processing, the output is exactly the same as the output would have been of the kind of original shuffler we cared about. Okay, so this is all post-processing. So again, for the purpose of privacy, we can just get rid of it. And now, again, the only information that survives is the number of ones, the number of one primes, the number of zetas. And the probability of these, the distribution of these, is a little different to the distribution in the intuitive example we gave. In the intuitive example, we gave a slightly worse version where x1 and x1 prime just said who they were. In this version, we get a little bit more privacy from them not saying who they are. They're going to say, you know, slightly biased version of who they are. Okay, so now we just have a multinomial distribution. It's a little bit more complicated than in the intuitive example, but marginally more complicated. It's still just a multinomial distribution on 3 outputs. And so we can do a fairly simple theoretical analysis of this multinomial distribution to get the bound that I guess I advertised at the top, which has this exponent of 0.5, which is what we really wanted. What is maybe more interesting, I think, about this result is that we get this asymptotic, so this is asymptotically optimal. We get this asymptotically optimal theoretical analysis, but additionally, we get something that we can analyze empirically really easily. So as long as n is not too large, we can just construct this distribution, the probability distribution of this distribution, pretty easily empirically, and empirically compute the privacy loss or the divergence between the distribution on P and the distribution on P prime. And this gives us actually tighter results. So what I have here is similar to the graph I had previously. So still on the y-axis, I have my shuffled privacy guarantee. This time on the x-axis, I have epsilon 0, or e to the epsilon 0 minus 1, which is kind of close to epsilon 0. And the red line is, again, this binary randomized response. So this is an exact computation for binary randomized response, which means it forms a lower bound on this graph. So the general result can't amplify better than binary randomized response. The green line is our theoretical result. So this is kind of our closed form solution, just kind of typed into Python. And what's interesting is this orange line is our empirical computation. So it's computed by computing those PDFs and computing the divergence between the PDF on P and P prime. And it is quite a lot lower than the theoretical one. The blue and purple lines are the best known prior bounds. So the orange one is always significantly lower than all of those. And for small epsilon naught, it looks very tight. And for larger epsilon naught, there is a gap between the known lower bound and the empirical computation of the upper bound. And we're actually not sure if that's inherent. So it's possible that binary randomized response actually does amplify better than the kind of general result. But it's also possible that there is just this upper bound can be tightened slightly. And right, so computing this empirically, we get much tighter results. And actually we're getting something that is both empirically tight, both asymptotically tight, and in some settings, genuinely empirically tight. Okay, so we did this proof just then for the non-adaptive setting, non-interactive. The proof for the interactive setting is not a lot more complicated. I'm happy to talk to anyone about it, but it's got enough notation that I'm not going to do it right now. Okay, so I want to finish with just a nice application, I think, of this result. So at the kind of top, I explained it that maybe you're just doing a computation and you don't want to work in the local model because you don't want to pay the accuracy costs. And you don't want to work in the central model because you don't want to pay the trust assumption. You don't want to pay the trust cost. And so we introduce the shuffle model to kind of get the best of both worlds. So what I'm going to give now is an example of a problem where we can actually use the shuffle model to get a accuracy that is the same as the central model with some kind of backup privacy in the local model. And this is going to be frequency estimation. So in frequency estimation, I just have a data set. I'm going to assume my data points lie in 0 to k. So I have a discrete data domain, and I have n of them. And I'm just trying to estimate the vector of empirical frequencies of this data set. Okay, so this problem is actually really well understood in both the central and local models of differential privacy. And our goal is going to be to define an algorithm or design an algorithm in the shuffle model, which has a couple of constraints. So the lowest one, the bottom constraint, is going to be the most important. So the error has to match the optimal error in the central model. We're actually only going to get that up to a factor of square root log 1 over delta. But remember I said at the beginning, these square root log 1 over delta terms are fairly small. So we can think of them as, roughly constant factor terms. We also want 3 other things. So we want our algorithm to have low communication. We want it to be a single message per user. So we're okay with an interactive algorithm, but we don't want that interactive algorithm to be multi-round. And we want to have some local DP protections. So these don't have to be like really good local DP protections, but we do want to have some kind of backup protection there. And remember, that is nice in case we have collusion between our shuffler and our central server. So a shuffle DP protocol that satisfies the final requirement was given in 2019, but it doesn't satisfy the other conditions here. And what we're going to show now is that using the privacy amplification for shuffling results, we can actually really easily get a result in this setting. So where prior to this might have worked quite hard, we can actually borrow directly from local DP results to get an immediate result here. Okay, so the algorithm we're going to borrow is from these 2 papers in 2019 and 2020. And they show that there exists a low communication single round epsilon 0 locally DP protocol for frequency estimation that gets the following guarantee. The particular guarantee we're not going to super care about in this talk. But what is important is that this is optimal. And we're going to care about the L2 distance. Okay. And now, to define our shuffle DP protocol, we're basically just going to steal this local DP protocol exactly. So we're going to define a local DP protocol on a permutation of the data set, or we're going to shuffle the local reports. And we're going to set our epsilon 0 to be this formula here. What's important about this formula is that when I plug it into the privacy amplification results we just gave, we get epsilon. So if you set epsilon 0 equal to this, then your shuffled algorithm is epsilon DP. And now, because we're just shuffling the local reports, we still have low communication. We have the exact same communication as the local DP protocol. We still have a single message per user because the local DP protocol had that. And we have some local DP protections. Notice this epsilon naught is pretty large. So remember earlier when we talked about why decreasing that exponent was important? It was important because sometimes we're going to care about large epsilon naught, and we're in that regime now. So epsilon naught is kind of epsilon times square root n. So it is quite large. It's not a great local DP protection, but it is something. And because of our privacy amplification result, we immediately get that this algorithm is epsilon DP in the shuffle model. And we immediately get this privacy error, this error. And we get this by plugging in epsilon naught into the formula for the privacy guarantee of local DP, the local DP protocol. And this is nearly optimal. The nearly is just because we have an extra square root log 1 over delta factor. But up to log square root log 1 over delta, this matches the optimal thing in the central model. Okay, so we really quickly with this result got this low communication single round algorithm in the shuffle model, and this didn't previously exist. So the best result previously in the shuffle model was the prior, the result I said for Ghazi et al. In 2019, that gets the same error bound, but doesn't have this low communication single round property. And the reason we can get this where prior results in the shuffle model didn't get it is because we've decreased that exponent and we've gotten optimal results in the large epsilon naught regime, where prior results were only optimal in the small epsilon naught regime. Okay, so I will wrap up there. For some reason my slides are funny. So just a reminder of what we did. So what we did was we showed that the shuffle model of DP, the privacy analysis can be reduced to the privacy analysis of this really simple non-adaptive mechanism. And that was important because it allowed us to do a nice theoretical analysis, but also allowed us to do an empirical analysis that gives us even tighter results. We gave asymptotically optimal analysis of adaptive shuffle in the approximate DP setting. Also, it's optimal in the local DP setting. And that allowed us to immediately attain an algorithm for frequency estimation in the shuffle model with nearly optimal privacy, utility, and privacy trade-off in both the local and the central model, and with low communication. I also want to mention, which I should have said this earlier, one other really nice thing about this reduction is that it's not, we focused on analyzing it in the epsilon delta DP regime, looking at the difference between those two distributions, the multinomials, for indistinguishability. We can also compute things like the Renyi divergence between them and get a result for Renyi DP, or we can analyze them in kind of the tails to get, or the moments to get concentrated DP. It's really flexible to computing whatever kind of privacy guarantee you care about. So if you're familiar with those other notions of privacy, we also get immediately empirical results there. Theoretical analysis is a little bit more tricky, but this really makes the problem a lot simpler even for those settings. Okay, thank you.
Yay. It'll unmute and clap. How do I do? There's a clapping emoji. This is all we get. Everyone's doing a clapping emoji. Yay. Fantastic. Thank you for the excellent talk, Audra. So for the audience, if you have questions, ask them now. I think you can unmute yourselves, but if not, I can unmute you. I'm still a year and a half later learning how Zoom works. So please ask your questions. Yeah. Or you can type them into the chat if you aren't comfortable. And I will start us off with a question about this, like a frequency estimation problem, which seems very practical, and I could imagine a lot of use cases. So this is kind of the most natural one, looking at things like, frequency estimation histograms. Do you think these techniques would apply more broadly to other types of questions? Do we have to limit ourselves to things like linear counting queries, or do you think this approach would be helpful in like a broader applications?
Yeah, so I think it should be helpful in broad applications. So the two, we also give like an SGD application in the paper, which I guess is still kind of in this fairly simple model. But yes, I don't have a good sense of how broadly you can get this kind of match between, like you can exactly match the central model. I'm not going to take a guess, I think, at how broadly that is true. But I certainly think that there is a really good reason to work in the shuffle model, and practically that's probably where we're gonna, I think the central model is very far off from industrial applications. So I think it's worth doing the work to figure those out. But yeah, I think so. I don't think there's anything really inherent about kind of linear algorithms or like simple noise addition algorithms. Here, those are just kind of, I guess, the low-hanging fruit.
Nice. Any more questions from those who are still here? I see like a bunch of people said thanks and bye. Okay, so I will stop recording.
Okay. I'm gonna